U.S. Agency for International Development. The U.S. Center, if you haven't been here before, is a public diplomacy effort put on by the State Department, which is used to show U.S. efforts both domestically and abroad aimed at combating, mitigating, and adapting to climate change issues. We have a very full schedule for the next 2 weeks, so before you leave, grab a schedule, one of these paper schedules in the back, and come check us out again because we're going to have a lot more interesting talks going on. What we are talking about today, right now, is an event titled The Latest on the State of Our Climate and Drought Monitoring. Our speaker will be Skyping in, or Google Hangouting in, I guess. His name is Deke Arndt. Deke is the chief of the Climate Monitoring Branch at NOAA's National Climatic Data Center in Asheville, North Carolina. He's served as the lead author of the 2009 BAM's State of the Climate Report and is a leading NOAA climate communicator. So we'll turn it over to Deke now.
Hi, everybody. How are you doing? Thanks for having me. Are we doing okay on the tech side? Okay. I'm going to press forward.
We can hear you.
Okay, super. All right. So we're going to talk today. I'm presenting on behalf of Dr. Jessica Blunden and Dr. Mike Brewer, who oversee different parts of our operation, in particular with collaborating with lots of international authors and data providers and analysts for various pieces of their work in the climate services world. So while we're going to be talking about the state of the climate today, much of this work from our end through Jessica and Mike and a little bit with myself is about where we'll be speaking about data. There is a great deal of international collaboration for both scientific expertise, for data sets, for monitoring, and so on. So the next slide, I believe slide 2, we're located in Asheville, North Carolina, which is in the south of the southeast United States, and we're one of 3 World Weather Libraries, the other 2 being in London and in Moscow. So all of the data that is observed from around the world from all the participating nations ends up in one of these 3 centers, and we happen to be the world's largest archive of weather and climate data. So a lot of what we talk about going forward in the next 30-35 minutes or so is built upon data that is stored both in this building and with several of our partners around the world. So slide 3, please. Today, this, again, a lot of great work and leadership done by Jessica and Mike in kind of 2 different worlds. Jessica has led the BAM's State of the Climate Report, which we'll talk about very shortly. She's going on her 5th year now, or 4th year, as the leader of that report, which is an international collaboration with many authors from many nations about assessing the state of the climate and really understanding and putting numbers on how the physical climate system is changing. Mike is our U.S. Drought Portal program manager. He's a climatologist as well, and the Drought Portal not only brings together communities to monitor and understand drought in the United States, but plays a big role in global coordination of drought communities, both monitoring and assessment in the drought world, and we'll talk about that in the last half of this presentation. Neither of these folks could be here today. Mike is with his family, and Jessica is actually in Switzerland. She's in Geneva putting together the World Meteorological Organization's annual statement on the status of the climate, which I believe is to be released in some way this coming week. I believe it's coming on Wednesday or Thursday, and it will be announced in the COP19 event in Poland. So they both send their best and their regrets for not being able to be here today. All right, so next slide. The first portion of the presentation today will deal with the State of the Climate in 2012 report. There is a URL. We'll provide this URL several times before the end of the talk, but you can download this report in its entirety and the 22 reports that came before it, the annual reports, at the URL that's shown on the screen. I want to acknowledge that this document is not, even though Jessica and I coordinate the authorship of this document, the content itself comes from about 400 contributors from about 50 countries around the world. It is not strictly a NOAA document. It's just we have the privilege of being able to coordinate and publish this thing. But lots of participation and expertise from around the world. All right, slide 5. Just a little bit of background on the report. Why do we do this thing? This is the 23rd year that we've put together this report. What this report does that's perhaps unique among the climate monitoring and assessment world is it really fills in a gap between month-to-month monitoring and assessment, which several institutions, including ours, the Climate Monitoring Branch, will do this kind of real-time survey of the state of the climate. And then we also have on the other end of the spectrum, about every 4 or 5 years, we'll get a large assessment report like that from the Intergovernmental Panel on Climate Change, the IPCC report. The U.S. government will commission a climate assessment to be released quadrennially every 4 years as well. What this report does is fill in the gap between those. So it is like the annual physical of the climate system. So when you go to the doctor for your annual checkup and you get lots of diagnostics on how the different systems within your body are doing, that's exactly the purpose of this report. It does not try to make large sweeping assessments. It does not invent new science. It strictly provides an update to the diagnostics, to the diagnosis of what's going on in the climate system. So we don't do attribution. We don't say this particular big event was caused by climate change. That's outside the scope of this report. What we will do for a big event is put numbers on it, characterize how unusual that big event was, and whether there's some kind of trend associated with that big event. And that is the purpose of this report. It is to provide, going back to that doctor and medical metaphor, it is to provide the patient's chart so that the research community can have a standard, up-to-date, annually updated set of numbers that come truly from experts around the world. This happens to be the 23rd year of this report. All right, slide 6, very briefly, it just shows a little bit about the history of this report. It has been led by NOAA since its inception in the very late 1980s. At the time, it was led by what is now called the Climate Prediction Center. And then about 13, 15 years ago, the leadership was handed off to our institution, the National Climatic Data Center, and we've managed it from there. But it has always been about the data. It has grown to be quite large, and we have, luckily, a great deal of international support and collaboration. But it always has and always will be about the data, and not necessarily breaking new ground on the research. All right, next slide. So who does this? It is truly experts from around the world. We are lucky to have, we had almost 400 authors and editors when all was said and done in this last annual report. And they came from 52 countries. And they come from around the world for a number of reasons. First of all, the regional aspect. You know, we love to have data and analysis about parts of the world from people that live in those parts of the world. So we have a strong regional component of this report, and we'll touch on that very soon. But we also acknowledge and we benefit from the fact that there are pockets of expertise throughout the world. So there are centers of excellence and centers of climate monitoring excellence around the world, and we try to pick off as many of these experts who can donate their time as we can. And it is a volunteer effort. None of us are paid, compensated for this. This is a service that we try to do for the climate monitoring community and the climate research community. So we are, again, fortunate to have folks from many disciplines. I happen to be a meteorologist. Jessica comes from more of an atmospheric chemistry background, but we have glaciologists and oceanographers and people that study stream flow, and we have just a really broad representation, a nice diverse group that come together and put this document together. All right, next slide should be slide number 8. I promise I won't read through all of this, but this is kind of what we're charged to observe. So in addition to wanting to get the report out on time and needing the report to be as accurate as we can possibly get it, we want to cover the broadest amount of the climate spectrum that we can. And so this large list of essential climate variables is our uh, baseline. This is what we're trying to achieve in terms of monitoring. These were established by the Global Climate Observing System effort, which is a World Meteorological Organization or WMO endorsed group that kind of has defined, if we were to accurately observe all of the things on this page, we would go a long way towards comprehensively knowing and quantifying all the aspects of the climate system so that we could put those things into climate models and really improve those even more. So from a monitoring standpoint, in this report, there are others that are monitoring things that don't go into this report, but in this report, wherever you see the color green, we feel that those are at least partially, and in most cases, fully monitored within the report. So one of our goals over time, and this is where we really need the international collaboration, is to fill out all of these essential climate variables, turn them all green for the purposes of this report. And a lot of times in our downtime, which is actually right now, we're about to spin up the effort to start the 2013 report in about a month. We'll be knocking on doors and calling people and say, hey, can you contribute your river discharge data for us, for example? So this is a living list, and we're constantly trying to catch up with what is most appropriate. All right, next slide, slide number 8. This is strictly just the layout of the report. So if you were to download the report or find a printed copy, each of these sections is a chapter in the report, and there are 6 major chapters. There's actually 7 chapters overall with an introduction, but these are the 6 major chapters. This is how we divide the report. We do like a lot of physical climate folks do, and we cut the climate system up into different pieces where it's easier to analyze, different parts at a time. And then I want to focus on the last section, the regional climates. And this is something, again, where we have the most international participation and leadership on the document. We have editors sitting thousands of miles from the U.S. that are putting together pieces of this chapter in particular that help us really understand what are the consequences of the changes that we're seeing. So the first 5 chapters that you see are strictly analytical numbers. We see this trend, we see this process, we see these kinds of changes. And then the regional climates chapter also details the events that occurred during the year and how those fit or don't fit into a long-term trend, and what are the costs associated with some of those events as well. So this is how the book, I guess, it's about 250 pages. This is how it's laid out. All right, next slide should be slide number 10, and this is a familiar slide. We presented this in the past, and we've seen this kind of take a life of its own in other places, but this is essentially taking the long-term major essential climate variables that we looked at a few slides ago, the ones that have data reaching at least back into the late 1970s, and how those are changing over time. So where you see a white arrow pointing up, that means that particular variable or phenomenon is increasing. And where you see a black arrow pointing down, that means that that particular variable or phenomenon is decreasing or getting smaller over time. And 2012 basically continued the pattern for all of these. And it turns out that for all of the values that you see here, those trends are entirely consistent with what you would expect in a warming world. So in a warming world, we would expect to see surface temperatures rise, and we have. We would expect to see sea surface temperatures rise, and we have. We would expect to see sea level rise, and we have. We would expect to see sea ice and glaciers and snow cover, anything dealing with the frozen part of the world, to decrease, and we have. And this chart takes the numbers off, but puts the context in the chapter. Where you see features colored in red on this document means not only is the 2012 behavior consistent with the long-term pattern, that also the 2012 behavior was either record or near record level. So for snow cover, particularly in the northern hemisphere, it was a record early decline in the spring season. So as we came out of the snow season and went into the snow melt season, By the end of the snow melt season, we had retreated farther than the snow line had retreated farther than we had seen since we've been taking accurate records, and that's almost 50 years. The Greenland ice sheet, the ice that actually covers the island of Greenland, again, record level of melt in that. Sea level, once again, pushed to a new high in 2012. Ocean heat content, very near the record value for the upper 700 meters, the slab of the ocean that's almost a kilometer thick, the topmost ocean. The amount of energy stored in that, again, near record levels. Sea ice in the Arctic, especially, record levels in September of 2012. It retreated farther back in its annual retreat, which ends in September every year, than it had since we've been keeping accurate records in the 1970s. And then finally, the temperature of the stratosphere, which is a little confusing, but in a greenhouse warmed world, we expect the lower part of the atmosphere to warm, which it has, at the expense of the upper part of the atmosphere, which is cooling, and it has too. So this above the halfway point in the atmosphere, the stratosphere is cooling, consistent with what we would expect, because greenhouse gases trap heat lower in the atmosphere at the expense of the temperatures in the upper atmosphere. And the stratosphere itself hit near record levels of low temperature in 2012. Again, all of these completely consistent with what we would expect, not only in a warming world, but in a greenhouse warming world. And those were the major findings. We'll go into some details about pieces of these, but if there's one slide to take away from the state of the climate, this encapsulates it pretty well. All right, next slide should be slide number 11. And this is just the global average temperature over time since the late 19th century. So 1880 is on the left side of this slide, and 2012 is on the right side of this slide. The blue crosshairs indicate individual years and how that global temperature for that year related to the 20th century average annual temperature. Above the zero line, those years were warmer than the 20th century average, and below that zero line, the temperatures were cooler than the 20th century average. And we can see that in the last 15 years or so, we've been hanging out in a very warm neighborhood relative to the last 130 years or so. So all of those crosshairs in the upper right corner of the slide represent, in many ways, a new normal in the global temperature. 2012 was not the warmest year on record. It was about the 10th warmest year, depending on which data set you analyze. Ended up being the 9th, 10th, or 11th warmest year on record, according to most data sets. 2013 so far would fit a little warmer than 2012. It would be about the 7th warmest year on record if the last 3 months of the year play out like the first 9 have. So we're still putting, of course, we're still observing those numbers, and we'll have a more comprehensive update. The WMO, the document that Jessica's leading, will have a provisional statement today, and then a more concrete statement in the early parts of the year, and so will be the National Climatic Data Center. Anyway, so that's what the temperature trends look like. And if we go to the next slide, slide number 12, this is what that single crosshair for 2012 looks like when you view it on a map. And areas that are in pink or red, those represent areas that were warmer than the recent history. Areas that are in blue represent areas that were cooler than the last few decades in 2012. And this is an important slide to show, because even in the warmest years that we have, there are still pockets of cold running around even over the course of the year. So here in North America, we actually had a very warm 2012. The United States itself had its warmest year on record, and Canada and Mexico were very close. And you can see that shows up very well on this slide. But you can see pockets of blue. Parts of Asia and Eastern Asia were cooler than the last few decades, cooler than the new normal. Alaska, the U.S. state that our western and northernmost state, was cooler than normal, and it's a cold place, so it had a cold year as well. So the sum of all of these colors, when you average them together, ended up giving us about the 10th warmest year on record. If we go to the next slide, this is basically the same data but presented in a slightly different way. So instead of comparing each box on that map with the 1981 to 2010 average temperature, for this map we're comparing each little box on the map with that box's own history. And where you see the darkest red, that particular box had its warmest year on record. And where you see the medium brand of red, or what we call much warmer than average, that means that that 2012 finished in the top 10% of its own history. And where you see the lightest pink, that means in the top third. So much of the globe, again, warmer than normal. When you look at the longer history, there's more red on the map because the longer history is cooler, and relatively speaking, 2012 stands out against that long-term history. We can see that parts of the Mediterranean, Southern Europe, much of North America, parts of South America and the adjacent Atlantic Ocean, and parts of the Indian and Southern Indian Ocean, particularly near Australia, had their warmest year on record. And these are for a box to be eligible for this map, it needs to have an 80-year history or more. So for those places where you see the darkest red, that means 2012 was the warmest of at least 80 years on record. All right, next slide is slide number 14, and we'll start to accelerate here as we go. A major event that isn't necessarily connected with climate change, but is an important driver of year-to-year outcomes, is the El Nino, La Nina, or ENSO phenomenon. And what we had in 2012 was, for the first time in several years, the year wasn't dominated by either the El Nino or the La Nina phase of ENSO. It was actually quite neutral for most of the year. We started the year in a weak La Nina pattern, but then transitioned pretty quickly into a neutral pattern, and that held and is still holding today. So we've had a run of more than a year in these ENSO-neutral conditions, and that is important because ENSO is a powerful driver of regional variability. And when we say variability, we mean how different seasons behave. Australia, the Oceania continent, the maritime continent, the Pacific, anything around the Pacific is pretty sensitive to this phenomenon. And the fact that it was neutral was an important thing to note during the year. All right, next slide, number 15, is zooming in on some of those ocean variables that we introduced earlier. Ocean surface temperatures, like much of the rest of the planet, were not the warmest on record, but they were in that kind of top 10 category, depending on the analysis. Again, upper ocean heat content, the actual amount of energy being stored in the upper 700 meters of the ocean, very near record highs for 2012. And then sea level rise. After a pause in 2011, we really saw a rapid rise in the global average sea level in 2012 and continues into 2013. So as far as big picture ocean conditions, this is what we've seen. All right, the next slide is slide number 16. These are atmospheric temperatures. And just a quick run through the system. These are for different levels of the atmosphere. So we should see three maps stacked on top of each other. The one at the bottom is the surface temperature. So the temperature at the surface of the ocean or the surface of the land, the part of the atmosphere that we live in. The next slide up is the lower tropospheric temperature. So the bottom few kilometers of the atmosphere. And the top temperature is the lower stratospheric temperature, which is this slab of atmosphere that's begins several kilometers up above the surface. So you can see as you go from bottom to top, generally warmer than normal conditions in the troposphere, and then very, very obvious cooler than normal temperatures in the lower stratosphere. Again, an example of in a greenhouse gas warmed world, we would expect to see the lower parts of the atmosphere continue to warm, and we would expect to see the stratosphere continue to cool, and we have. Again, the warming is confined to the lower part of the atmosphere at the expense of the upper part of the atmosphere, which is exactly what you would expect, and that's exactly what the data show. All right, next slide is slide number 17, and we're talking about changes in greenhouse gases. These are the gases that are driving this long-term big picture change in the temperature of the global atmosphere. And we saw that carbon dioxide threatened the 400 part per million mark in 2012. Several observatories did see an average value above 400 parts per million, but when we took the average globally, it came in just shy of that. Methane and nitrous oxide, a couple of greenhouse gases that are much smaller in concentration, but important because they're very potent, also continue to increase. And when we take the kind of aggregate sum of carbon dioxide, methane, nitrous oxide, and several other trace greenhouse gases, we see that the amount of additional warming at the surface that those gases are contributing is now almost 3 watts per meter squared, which is a constant additional provision of energy to the surface of the Earth, and that's up 32%. So essentially the greenhouse part of the atmosphere is now about a third more potent than it was back in 1990. Again, as these greenhouse gases continue to increase in their concentrations, the expectation and the data bear this out so far is that they will continue to warm the lower part of the atmosphere by trapping heat. All right, next slide. I want to focus on the Arctic before we finish up with the state of the climate piece. The Arctic has been long predicted to be an area, a region that is going to change more rapidly than the rest of the planet. And that has to do with the fact that there's a lot of ice up there that is very near the melting point, and there are a lot of these, what we would call positive feedback or vicious cycle type activities, where if you push the system to be a little warmer, then ice melts, and that contributes to the warming even more. And so we see a lot of those kind of scenarios in the Arctic. And you know, we hear about sea ice. In 2012 was a huge year for Arctic sea ice. It was just destroyed the previous record, and that's important in and of itself. But you know, one of the things that Jessica and I really realized when we read this Arctic chapter that these experts had put together is, you know, it drives home that the Arctic is a system of systems, and it's not just sea ice. We're seeing dramatic, rapid change in many aspects of the Arctic climate system. So the next few slides are going to look a little bit about those different angles of the change in the Arctic. All right, so slide 19 shows or presents some information about both the changes in what we see in the permafrost, and I'll come back to that, and then also in the amount of ice represented in our world's glaciers. So permafrost is permanently frozen ground, and what we're seeing, especially in North American and Russian near Arctic and Arctic places, is that the permafrost is thawing, and the permafrost that isn't thawing is tending to get warmer, and we're seeing more and more permafrost, permanently frozen ground below the ground, kind of participate more in this melt freeze annual cycle. So we have less the layer at which, the depth at which ground is permanently frozen, for the most part, is increasing, and more of the previously permanently frozen ground in the Arctic is participating in a seasonal melt thaw cycle, or thaw freeze cycle. For glacier mass, this is about the amount of ice that's sitting on top of 30 glaciers around the world. They're kind of composited to make an index. And 2012 saw yet another year of large ice mass loss in these glaciers. So what this graphic shows, each individual bar is the amount of ice, or the water equivalent of the amount of ice that was lost from these glaciers. And then the single red line is the cumulative total, and it refers to the right-hand axis. So the punchline is, in the last 15 years, we've taken an average of about 8 meters of water off the top of these glaciers. That's how much ice has been lost from these glaciers. 2012 will be the 22nd consecutive year that we've had a net ice loss on these glaciers. All right, next slide. Slide number 20, this deals with Arctic amplification, which was what we talked about a minute ago, and this expectation and observation that the Arctic's going to change more rapidly than the rest of the Earth. And we've seen that when you compare temperatures in the Arctic in recent years to its own history, the changes are much more dramatic than the rest of the planet. And that is, again, expected. It plays out in the observations. In general, there are some regional variations. Temperatures in the Arctic are warming at about twice the rate as the rest of the planet. Slide 21, please. We saw several records. Again, the Arctic isn't just about sea ice, and we haven't got there yet, but we saw permafrost temperatures threaten records, and in many observatories break records. We saw spring snow cover extent. So coming out of the winter into the spring transition season, we saw the snow retreat more and more rapidly than it has since we've been keeping records for about 50 years. The end of summer sea ice cover, sea ice extent in September, well documented, just demolished the previous record, which was set in 2007. The amount of ice lost from the Greenland ice sheet was record value during 2012. Ice breaking up in the lakes in the Arctic and near Arctic, also near record levels. And then specifically in the Canadian portion of the Arctic, glaciers and ice sheets in those areas, again, record levels of loss as well. So it wasn't just sea ice. The Arctic as a whole, and sometimes it's difficult to connect what's going on in the Arctic into our everyday lives, but we are seeing dramatic changes, and it's not just in sea ice. It's in a lot of these physical climate systems, and as we'll see in the coming slide, it's in the biology of the area too. So if you go to the next slide, please, it's number 22. So we saw this large record sea ice extent value in 2012, and that has consequences because the less very bright reflective ice that we have in the Arctic, the more sun the planet absorbs up there. And again, to this positive feedback or vicious cycle kind of cycle, less ice means more sun absorbed, which means more warming, which means less ice. And it's kind of this reinforcing process. But what it means, and that's what it means in the long term for the planetary and the Arctic temperatures, but what it means in the short term is that there's more exposed water. And when there's more exposed water rather than ice-covered water, we see coastal impacts because the wave action is different and typically stronger. We see more phytoplankton, green living phytoplankton in the ocean. So the ocean color is greening up in the Arctic quite a bit. And that's what the picture on the right shows. Where you see green, that's a measure called net primary productivity. It is essentially a survey of the volume of the plant life, the basic phytoplankton. It's the bottom of the food chain, rapidly increasing in parts of the Arctic. And when we see phytoplankton increase, we're going to see a big impact on living systems for more complex animals and plants as well. The other thing that we've seen in the Arctic is a great deal of what's loosely termed the shrubification of the Arctic. So in the tundra in the Arctic, where we would typically see grasses and sedges and lichens and very kind of small, compact plant life, we're seeing more and more bushy, tall grass and bushy growth in the Arctic as well. So ecosystems are changing both on land and in the water, and this is rapid change. And there's a great deal of research work to try to understand how are these ecosystems going to play out in this rapidly changing Arctic, and how are the human systems, which are, human infrastructure is really, really impacted by increased wave action up there. It's really, really impacted by a more dramatic freeze-thaw cycle up there. So Canadians and Americans and Russians and Norwegians are dealing with pipelines and roadways and human infrastructure that is subjected to a much more dramatic melt-thaw cycle than it used to. Also on coastal and offshore interests, there's much more wave action in recent years than there used to be because there's much more open water. And so these are both economic and ecological concerns that are kind of attached to and lumped on top of the physical climate system and how it's changing. Jessica and I won't pretend to be the experts on all of these connected aspects, but again, putting this report together to try to put numbers on what's physically being observed hopefully informs the world's thought leaders that are trying to make decisions on how to support human infrastructure. And many of these decisions are multinational, bilateral, trilateral, multilateral as well. So we hope this report serves those kinds of decisions. The next slide, slide number 23, I just wanted to point out that that second blue bar from the right, that's the 2012 Arctic sea ice extent. That was easily a record value. That bar dipping down very low in 2012 represents the smallest ice footprint that we've seen since we've been keeping records in the 1970s. At the same time, the Antarctic has shown 2 straight years, 2012 and 2013, of a record maximum sea ice extent at the same time. So the Antarctic sea ice sheet, at least the seasonal growth of it, the last few years has been very large. And it's interesting, the Antarctic is a completely different kind of animal than the Arctic as far as sea ice extent goes. It tends to be kind of cut off from the rest of the planet. And I think we show this on the next slide, slide number 24. So there's, because the Antarctic is a continent surrounded by water rather than water surrounded by continents, it tends to get cut off by this, what we call the circumpolar vortex, represented in those yellow lines. So what happens in the Antarctic tends to be insulated a lot more. It's not as connected. It's not as directly connected to the rest of the climate. It's not as sensitive. We tend to have growth and then retreat, and much of the Antarctic is 1-year ice, where the Arctic is multi-year ice. And so a lot of folks always ask, well, why don't you pay as much attention to the Antarctic? It's just as important a place. And the answer is yes, it is indeed just as important a place. But the sea ice extent itself is less connected to the multi-year trends. It tends to be connected to what's happened this year. The part of the Antarctic that kind of creeps into the lower latitudes, or at least gets close to that, is the Western Antarctic. And that's the area with the little red highlight circle. And that part is warming. That's the piece that kind of sticks out and kind of plays with the rest of the climate system. And we are seeing temperature increases in Western Antarctica. All right, so the next slide is slide 25, tropical cyclones. In 2012, it was the 3rd straight year of a relatively low number of tropical cyclones, coming off some historic lows in 2010. The last 3 years, 10, 11, and 12, have seen lower than average numbers of named storms. The two, for the second consecutive year, both 11 and 12, 2011 and 2012, only the Atlantic Basin, that which impacts Central America and North America, was more active than usual. All of the other global basins had less than normal activity. 2 of the year's most notable storms were Hurricane Sandy, which caused a lot of damage and destruction in the Caribbean Sea, and then again in the northeastern United States in October, and Super Typhoon Bhopal, which caused a great deal of destruction in the Western Pacific. And we're seeing again an event just in the last week that's very similar and possibly even larger than Bhopal. Important to note, the connections between individual storms and climate change is still actively being researched. So what caused a particular storm to be as intense as it was and to take the path that it did? A great deal of work has to be done to connect the climate system with those individual events. But what is not in doubt at all is that as we raise the level of the seas with sea level rise, a storm will cause more damage due to storm surge as it operates on top of a rising ocean. In particular, in near the Philippines, we're seeing sea level rise outpace even the average for the rest of the planet. And so storms that hit in that particular part of the world are working on top of oceans that are higher than they were just a couple decades ago, and they're continuing to increase. All right, so that's that. So I wanted to focus as we wrap up on the regional climates. This is the chapter 7, and it's a great chapter. It's a nice reference of what happened around parts of the world over the course of the year. a particular emphasis on big events and when they happen, and meteorologically, kind of what were the drivers and how did they affect people and how do they fit into a larger pattern. And Jessica's been fantastic about, and our regional chapter editors especially have been fantastic about recruiting more and more folks from around the world. So the next slide, slide number 27, this represents countries colored in green are countries in which a professional from that country actively participated in the State of the Climate document. And while we have a long way to go, and we really want to encourage, in particular, authors from Eastern Europe, from Africa, from Southeast Asia, and from parts of South and South Central Asia to participate. We would love to have more participation from those parts of the world, and we think our document will be better when we do get participation from there. This map is a lot greener than it ever has been, and we're very proud of that, and we hope to continue to spread that color throughout this graphic. We've seen, and you can see them on this map, continued participation from professionals who are undergoing major changes in their country's governance, and they're pressing on and continuing to provide data and expertise. And we feel our document is much better off for that, and we're very thankful for their dedication to their discipline. The next slide, slide number 28, is instead of the countries that are contributing authors, these are countries that are explicitly addressed in that regional climate section. So there is data that speaks to each of these green countries in the State of the Climate document. Again, this is more green than we've ever had, and again, we have a long way to go before we feel like we've completed the building out of this regional chapter. So the next slide, to just summarize a few events. In any year, even a very warm year, you're going to have episodes of extreme warmth and episodes of extreme cold. Here are a few of them. We won't go through every single one of these. North America probably was the warmest, relatively speaking, compared to the rest of the world. But we had some very, very warm years and very, very warm summers. And I think you can see there's quite a spread of where these things happen on both of these. That cold episode in Europe in February, early February, was huge. It was the coldest snap that we've seen, or that part of the world has seen, in several decades, and it caused quite a bit of suffering. So that we do, even in a warm year, we'll see these episodes of big cold. All right, next slide is slide number 30. And we're going to probably go through this a little quickly because we have a couple slides following about drought. But I wanted to emphasize that that top box lists several areas that were prone to droughts. And one of the things that we saw in 2012 was a lot of the major grain producing areas in the Northern Hemisphere really, really suffered with drought. And we're seeing global economic and food security consequences of losing big pieces of those global grain market. So not only does the price of grain increase, but that is the stuff that feeds livestock, and that contributes to increase in the cost of livestock, and so on. And so we saw in North America, in parts of Eastern Europe, in parts of India and South Asia, and even in Australia, major grain producers really took a hit with drought in 2012. It's probably the story of the year. It may compete a little bit with the sea ice extent in the Arctic, but this kind of massive, and especially in the Northern Hemisphere, composite drought was a big deal. Slide number 31, that's just the U.S. temperature. It was easily the warmest on record. It was a full degree Fahrenheit, or a little more than half a degree Celsius warmer than the previous record. The next slide is slide 32, and this is starting our little 5-minute excursion into drought. We've been dealing with a big drought in the U.S. since about 2011. It peaked in 2012. It has thankfully improved somewhat in 2013. But again, a lot of the area that you see in red and in color here are the major grain producing areas of the United States. One of the things that we found on slide 33 was that the temperature that we had in spring and summer contributed to making the lack of precipitation part of the drought even worse. So not only did the rain turn off, but it got very warm. And when it gets very warm, the atmosphere will ask for more water from the soils. And so we had that composite effect. Not only did we have a lack of rain, but these maps show for particular droughts how the heat impacted and made the existing drought even worse because it evaporated what little was left in the soils. And that was slide 34. And if we can go to slide 36, we'll touch on drought and the Global Drought Information System Initiative. It's the same punchline. We're looking for regional participation in the Global Drought Information System. So slide number 37 shows that drought is a global phenomenon. It's a natural part of our climate system. It's a natural part of our human experience, but it occurs and it's costly, and it can cause significant concerns when drought happens overlaid with food producing areas and overlaid with parts of the world that are struggling with other issues as well. So monitoring drought globally is becoming more and more important and more needed in real time. So the next slide shows some green and orange circles, and it shows that in the grain world anyway, the world's grains are grown in not necessarily grown where they're consumed. So where you see large pockets of orange, those are net exporters of grain. Where you see green much larger than orange, those are net importers of grain. And what we saw, if you'll notice where the big orange circles are, we'll walk through a couple slides pretty quickly. So we'll hit slide number 39. When I introduce the Global Drought Information System, the URL is there below. And this is a place where nations and continental scale monitoring, it's a portal to serve up the content from different efforts around the world regionally in monitoring drought. So if we go to slide number 40, where you see red dots in April 2012, those are areas that were struggling with drought. Many of them at the time, Europe was particularly hard hit with a lack of precipitation. But in this graphic, you can start to see issues in Mongolia and in parts of Russia. Again, these major grain areas in Russia. The next slide is slide number 41. By June, you can see lots of brown dots in Australia, in North America, in India, in grain producing areas of Russia and Asia. And that happens to lie, next slide please, number 42, exactly where the grains in the world are produced. So this is a play-by-play from the Global Drought Information System of what we saw in 2012 and how it overlays with the grain-producing parts of the world. The next few slides, slide number 43, shows that, again, major grain-producing parts of the world struggled with drought during 2012. And thankfully, by the next slide, number 44, it had improved by December of 2012 as well. And we're still, next slide is September. It is not as bad as it was in 2012, but we do see some emergence, especially in hanging on in the American Midwest and in parts of Russia and in parts of Southeast Asia as well. And then finally, what I'd like to show on the next slide, 46, is just some examples from the Global Drought Information System of some tools that they serve up. This is run through NCDC here in Asheville, but the data and the analysis especially comes from around the world. So we're not doing additional analysis on drought conditions here. We're essentially brokering and serving up what people in the regions are reporting and assessing as they go. So this is a tool that shows drought on the next slide, slide number 47, and we'll move on to slide number 50, if you don't mind. I apologize for doing this to you. But what you see on slide 50 are 4 different analyses for 4 different continents, and we've had Eurasia as one. That's the European Drought Observatory and their analysis of Eurasian conditions in drought. For Africa, we see an analysis from the IRI folks in Columbia University. The Australians are leading an effort in Australia and New Zealand to characterize drought conditions there. And then we have a North American collaboration between Canada, the United States, and Mexico to depict drought. As you can see on this map, we all do it differently, and that's a good thing. We all know our own local issues, our own local drought, our own local responses, our own local multilateral collaborations on water. But this information system brokers these and brings them together to give a bird's eye view of where drought's going on. If you wanted to drill down into the details of what's going on in Australia, this drought information system would send you all the way to their web space and let you read their analysis rather than trying to add value here. So the next slide, slide 51, is a layer of precipitation analysis. These are tools that are provided to all of those communities here through NCDC. It is not a declaration of drought. It is not a declaration of emergency. It is strictly data to support people in the regions who are making those important decisions themselves. And with that, I think I would move all the way through into the last slide to thank you for your time. And I'd like to stop there and talk with you folks.
Okay, great. Thanks, Deke. So we have quite a few questions from Twitter, so I'll ask one of those first, and then I'll transition over to a question from the audience.
Okay.
So one of the questions on Twitter is, should the link between drought and temperatures be seen as a positive feedback like ice in the Arctic?
That's a great question. So regionally, yes, it's the case. In the warm season especially, and especially in the interior parts of continents, when we see warmer temperatures, we often see a lack of precipitation. So, and as we warm in the long term, we are asking more and more water from the soils. So I would say kind of provisionally, regionally, with some caveats, yes. And it happens to be that many of the grains of the world are grown in the interior parts of continents, and they mature during the warm season. So we do see issues, and in 2012 was a great example in North America. Both the United States and Canada dealt with severe blows to their grain crops, not only because the rains turned off, but because it was quite warm. And then when you're in the summer months, the less moisture you have in the soil, the sun's energy can do two things. It can evaporate water from the soil, and it can heat the soil. And when you have less water to evaporate, when you have dry soils to begin with, more of that energy goes into heating the soil. So that was a long-winded way of saying yes, we do see that on a regional and seasonal scale, and to some extent on the long term, especially in the interior parts of continents.
Okay, any questions from the audience? All right, please state your name and affiliation.
Hi, I'm Farilde. I'm from an NGO. And my question is how you derive the data. There are also ways to derive data, for example, on biomass with remote sensing data. Why don't you include that in the report?
So in many cases, remotely sensed data is included in the report. We use lake temperatures, several vegetation and greenness indices are in the report. We aren't all the way there. One of the limitations of remotely sensed data is that the born-on date is usually the 1970s at the earliest, and often we only have 10 or 15 years of good data. So we want to connect that with that long-term in situ data, the station-based data. But I think if you read the global chapter, especially chapter 2, it's divided into 3 components. One is a traditional weather variables section. The next section is the atmospheric composition section. And then the third section is what we call terrestrial, and it's edited by Han Dolman from the Netherlands. And he is doing a great job of incorporating more and more information, remotely sensed information, into that part of the report. So biomass burning, vegetation indices, lake levels and temperature that are expertly sensed with remotely sensed data. A lot of what's in the report maybe didn't make it into my presentation today, but there is some information there, and we're trying to get better about including more and more.
Okay, any other questions from the audience here?
Hi, this is Georgia. Deke, you mentioned earlier that you're interested in increased participation from other countries. If folks are interested in doing that, what would you recommend that they do?
So there's hopefully we're on slide 63, and there's some email addresses to contact us. Jessica Blendon's the lead editor. I'm her co-lead. We can get you in touch with the appropriate folks for the regional chapter. And what we typically have around the world, we either have university-based climatologists, or we have folks that are in operational meteorological services. So what we call the National Weather Service here in the U.S. Every nation has a hydrometeorological service in their nation, and so we have a lot of professionals from those agencies as well. If they want to participate, and we want them to participate, if they agree to participate in the BAM State of the Climate Report, we'll get them in touch with the regional chapter editor for their region. So cmb.contact@noaa.gov, that'll hit both Jessica and me. If a country or a nation or an interest wants to participate in the regional aspect of the Global Drought Information System, it's a little more structured, and we would so there's nidus.questions@noaa.gov, and that will get to Mike Brewer and a couple other people who are working on supporting this Global Drought Information System. It is a little more structured. The WMO, the GEO, the Group on Earth Observations, they're trying to make the decision-making and coordination capacity at that regional and continental level. And so you would probably, although you could contact us, and we encourage you to do that, I wouldn't be surprised if we responded with, oh, the folks in your part of the world that are trying to get something together are such and such and so. And we really, for that piece of the puzzle, we really want that, and the WMO and GEO as well, want that coordination to be at that regional continental level. So groups of countries that make up a continent or part of a continent.
Okay, thanks. Good question. We have time for one more. Okay, I'll ask one more Twitter question. And that was, how do percent changes in temperatures compare to percent changes in climate buffers such as ice? So is there sort of a one-to-one correlation?
Yeah, there's not. It's totally it's a nonlinear system, meaning it's chaotic, meaning if you nudge one piece of the system up 10%, you're not necessarily nudging it all up 10%. These have connections that are dynamic and nonlinear. So for a great example is in the last 15 years, the global surface temperature, we haven't seen that large of an increase in it. It's kind of hanging out in this new neighborhood, and it's much warmer than the past, but we haven't seen a continued increase in the temperature. But at the same time, we've seen large increases in sea level. We've seen huge decreases in the amount of frozen stuff in the northern hemisphere. We've seen patterns in the ocean with salinity, where the fresh parts of the ocean are getting fresher and the salty parts of the ocean are getting saltier. And that is connected with the dry parts, the low precipitation parts are tending to get drier, and the high precipitation parts, the fresher parts of the ocean, are tending to get wetter. And so it is definitely not all marching at the same rhythm in change. What we're seeing, just like in our own lives, just like in our own families, we're seeing a long-term change in the global climate system, and we're seeing pieces of that climate system surge out and change more rapidly, and pieces of the climate system kind of lag back, and for example, the surface temperatures. So it is a dynamic system. These feed into each other. We would not expect them all to increase at the same pace, and we definitely haven't seen that so far as well.
Okay, great. Thanks, Deke. Thanks for taking the time to talk to us over in North Carolina. And if we could have a quick round of applause to thank him. And I'd also like to thank all of you for coming to the center. Up next, we have a presentation, Eyes on Earth in 3D at the NASA Hyperwall behind you. It's pretty cool. If you haven't seen this 3D production before, I recommend checking it out. And then at 6 o'clock, we have a presentation from the U.S. Carbon Cycle Program on U.S. interagency and international collaboration on carbon cycle science. Plus, as I said, we have a whole packed schedule for the next 2 weeks, so grab one of these brochures on your way out and make sure to come visit us again later. Thank you.